Yes, I'm going to be talking about the Karabo control system. My name is Stefan Elf from the European Expo, and Karabo is a full-fledged SCADA control system, which hopefully we're also about to open source. Just a brief outline of my talk. I first want to give a short introduction to the European Expo, but from a data perspective and control needs. And I'll talk about the framework itself, obviously, and conclude with a few highlight examples from how the system is used at the facility. So this plot we've already seen earlier today. That is the relative peak brilliance of light sources compared to the first X-ray tube over time and transistor count and processors. The reason why I like to put it up here is if we say that for each photo more naively, we can collect a bit more data we can analyze. It kind of shows that we reached a point where throwing more hardware at the problem might not suffice anymore. But we actually need to invest in smarter software, which often is analysis software, but also acquisition and control software, of course. Another high-level overview, just to orient us. Karabo is the control system at the photon systems and the instruments at the European Expo. The facility actually uses another system for the accelerator, which is DOOS, the Daisy Object-Oriented Control System. Both systems interface quite nicely with each other nowadays, so you can transport data from one to the other quite transparently with minimal effort. So all that is in orange here is covered by today's talk, at least at once. One other unique feature of the European XFEL, which is of interest for its control system as well, is our punch structure. So we can have pulses up to a 4.5 megahertz repetition rate. But these are arranged in bursts of up to 2,700 pulses each, so-called trains. So most hardware controlled by Karabo actually operates at this 10 hertz phase frequency, although we do have to handle data from detectors, which can take up to 4.5 million images per second burst as well, which leads to quite some high data volumes. So let's have a look at these data drivers. I'm not going to go through the details of this table, but kind of shows you. For the detectors that can image at 4.5 megahertz, we could get up to 10 gigabytes per second on data, which the control system needs to ingest in this burst, 10 hertz burst frequency. We've got custom-made FPGAs and digitizers where we go up to around a gigabyte per second. We've got a bunch of commercial cameras in all flavors. Luckily, mostly from FASA, so at least similar APIs, where we reach about 100 megabytes per second on the 10 hertz burst, and then 90% of the facility, that's what is often called slow control data, interfaced frequently through PLCs, but also through directly through manufacturer protocols. This is mostly event-driven at Expo, so we have average data rates of a few bytes per second to a few megabytes per second there. Putting that all together, we have Karabo on top, which connects all these data sources and controls them. This is actually a network graph for the MID instrument, showing kind of the internet connection between the various pluggable components. And if you inspect it a bit, you see features like our central timing provider, online calibration pipeline for one of these megahertz capable detectors, or the whole world. So that's what we need to control. And I'm going to talk about what we developed in-house to control it. Maybe start off with a bit of a motivation, why yet another control system. And disclaimer here. So this is a survey done in 2010, which I just had my 10 years anniversary at the facility, so that even predates me a little bit. But back then, people studied which control solutions exist and if they were capable of handling megahertz data acquisition, control itself, and slow control logging. And EPIX wasn't really found suitable for the DAQ, and Tango was just a bit still deciding where to go. So the decision back then was made to develop yet another control system, which first was named Excel Suite, but soon renamed to Karabo, which is Swahili for the answer. From the architecture point of view, Karabo is an event-driven system, basically around a central message broker. Currently, this is open in queue. It'll soon be interchangeable. We'll actually be testing other technologies this winter. Event-driven means data propagates through the system when values change, push, not pull. And it's message driven, follow the signal slot paradigm. Those of you who know Qt will be familiar with that. So a signal can basically trigger any slots to be executed. It's fully asynchronous in its core, but there's synchronous convenience in the middleware provided. Of course, the large data rates I mentioned earlier, 10 gigabytes per second, you don't necessarily want to pipe through a message broker. So we also have pipeline to TCP connections for scientific large data, which get negotiated through the broker though. We've got a central gateway server called the GUI server for our graphical user interface clients, which are also the main ways of interacting with the system. And another distinguishing feature is it's a fully dynamic discovery topology. So all the components on the system describe themselves. You do not need a central database instance for the system to run in principle, although we have one which I'll show later, configuration management. To actually provide functionality in the system, there's 3 APIs, one in C++, 2 in Python. And through this, we create what is called devices, which run device servers. These again run system servers on daemon tools over the distributed system. And yeah, so one slide here, maybe if you want to control something, you need to expose some data. We support the main data types, maybe a few highlights to mention here as well. There's support for composition and compound data types. We have multiple dimensional data built in, and also natively support tables actually as tables, and there is some workaround at hack to create them. This is all put in what is called the Karabo hash, which is an ordered recursive key value containing with attributes, where you can put all this in and it serializes to XML in binary format. There's also a state data type, which internally is a string representation, but describes a fixed set of states, which all derive from 3 base states up here. And because we have a fixed set of states in this hierarchy, we can actually do nice things like assigning a consistent color in any graphical user interface to them, or also evaluating in a straightforward way which state should be most significant if you have a bunch of them. That, for instance, an error state will always be shown. Also, quite a highlight of the system by now, it's data logging, which we do into Influx right now, Influx time series database. Distinction here is data logging versus data acquisition. For us, data logging is really continuous slow data from the broker for all devices. It's always done by default. All data acquisition is run-based, and you really explicitly have to start that. And the data acquisition would also include this large and fast data I'm talking about. We've got 2 logging systems right now. One is a text-based logger we first used, now as a fallback, and then Influx time series, which has been so successful that we use it as a monitoring technology via Grafana for our so-called data operations center, which provides support to all data services at the facility during user operation. There's a talk by Galo on this tomorrow with much more details. Now I mentioned 3 APIs. Let's go through those in a bit more detail. Well, generally, I say the framework is event-driven, asynchronous, and self-description, so that you'll see in all 3 APIs. But here's a bit on how they look. C++, C++ 14 and Boost mainly, smart pointers a lot, very template heavy. And you define properties on the system like this, so you always have kind of a type here, a key, and then you have the attributes which further describe it. The Python bound API was the first Python API we implemented that basically binds C++, the C++ API we use Python. It's not very Pythonic, if we're honest. It was aimed originally at high data throughput devices people wanted to develop in Python. If you look on the right, this actually looks a lot like the C++ I just showed, and that's on purpose. I want to spend a bit more time on examples is actually our middle layer API. So that's built on Python async.io. Like we consider it quite Pythonic. Its distinguishing features, easy interaction implements with devices across the distributed system. So here, properties are really just class level attributes. You have keyword arguments to define the attributes on our parameters, and you can use, for instance, decorators to expose a setter function here. If you want to expose a function call to the distributed system, you just have this lowercase slot if it needs to take parameters and return something for internal. If you were to use an uppercase slot, it would be visible in the GUI, but as a button command to click, that you couldn't really pass parameters to it anymore. Pipeline channels for moving large data around. Similarly, we just use decorators to mark what does what. And these proxies, well, this is an example of how to just control another device on the distributed system. Here in a command line interface, so synchronous, but also would work with context managers asynchronously. So you get the device, and then it's basically just an object where all the properties and commands are just on that object. No need to worry about that this is in fact on a completely different host or somewhere else. The middle layer API being so concise, then over time also led to us really using it to implement most functionalities. So that's the current share. And you see it's really outpaced the other two APIs and new implementations we do quite well. Another big feature of Karabo is the GUI, which is a generic tool. It's a separate Python package matched to the framework built on PyQt5 and connects via the central GUI server. The distinguishing feature here is the GUI scene builder, which is creating panels without programming. I'm not going to go into too many details as Dennis has a poster on this tomorrow, but that's an incomplete selection of the widgets which just come shipped batteries included basically onto a scene. You don't need to code anything for this. This is what at Xfile usually system operators just create. The nice thing is you can link this and then you get synoptics. So left side is scene linkage between the SASA1 tunnel topic, right side is one of our instruments, and again, you can inspect this a bit and then you see what the scientists came up with for navigating between different views. The SPB instrument is located on the SASA1 tunnel that feeds it, so there's even a link here to basically exactly that scene there as well. I did mention a bit, we also have configuration management, even though we don't need a central database for the whole thing. That is also done via so-called projects implemented in the SQL database. Good. So last few minutes, I just want to show a few highlights on how this looks at the European Exfile facility for the different APIs. One is our backup interfaces, so that's what interfaces to PLC. What you see here is a beamline overview. Most of this is this kind of flow control. This is implemented in C++ right now. It's a bit special in the sense that the PLC itself has a protocol which self-describes all its components. So in principle, our implementation can create a fully functional interface just by the PLC having something deployed. That's not always very convenient, but it is usable. And this is event-driven, then you can handle up to 1 kilohertz updates from singular devices. When we're coming to large data, this is now online calibration for Egypt, for instance, implemented in Python bound middle layer API, uses CUDA underneath. Well, and that can do online correction of up to 4,000 images per second. So here we're at the 10 gigabyte, 15 gigabyte per second data rates. This is of course not on a single host, but in parallel, as you can see a little bit through this overview table here, and right, you see the individual 16 modules of one of these detectors. Yeah, then of course we need to do some data acquisition. That's our VAQ, also C++, Boost and HDF5. Here we're investing up to 20 gigabytes per second in the control system. Can basically store anything that is exposed in the distributed system, ends up in HDF5 with that structure. And then center you see the operator interface for that. And then maybe one highlight from the middle layer, where we have a virtual motor base. So basically this is the pseudo axis, which Matthias just also talked about on our end. And there, this abstracts individual motor interfaces can act on multiple motors at the same time to provide coordinated motion. And this uses these processes I briefly introduced for the middle layer API a lot. Yeah, then already pretty much out of time. I didn't present many of the features we have. You see them on the left side, access levels, schema system, logging levels, interchannel brokers, schema injection, web proxies, and more. But there are some more contributions at the conference. I already mentioned Gail will be talking about influx tomorrow. Dennis will have a poster on the GUI. Ivas will present the scan tool on image annotation from a metadata in the Karabo GUI, which covers GUI extensions we can implement, and then finally integration and synchronization with commercial cameras in the poster. I also did not talk much about these devices, so where the actual functionality comes from. That's because we currently have about 300 projects hosting those which are active in our Git repos. That's more than 400 devices because there's multiple ones in some. Many of those are small. You see an excerpt from the table we have on the right, but some are big with 50 kilolines of code, for instance, for Pekov. And there's many contributions there as well. This includes, for instance, also integrating sticky devices in a generic way, and all these sorts of things. So, in summary, yeah, we've been developing the control system at Expo for the last 10 years. For the last five years, it's been running the facility, at least on the photon side and instruments. Pretty stable nowadays, can routinely handle tens of gigabytes of data per second coming through. It's scaled quite a lot. Next steps are, as I mentioned, we want to bring in public domain. So I would really like to show now a GitHub address here, but right now still dealing with how to GDPR compliant expose a GitLab commit history. And that will hopefully soon be done. And yeah, we want to look into authentication authorization. That's where the GUI server will come in handy. And also higher level configuration and web services and web GUIs. My last slide, already mentioned 10 plus years of work. There's been a lot of contributors. Like I said, watch out, it should soon be released. Thanks.
We've got time for questions. So maybe one hour. Not very technical, but why do you say you have to make the Git logs GDPR compliant? I never heard that.
Yeah, don't. I wish I wouldn't have heard it either. But our legal group is adamant about that. We do that in the proper way. So the commit history contains usernames, email addresses, and whatever of people who are not at the facility anymore. It's not a big hurdle, but it is one which one needs to consider. It seems that hopefully will be fixed.
Another question?